Hello everyone, I am Prateek Kumar. In today's video we will discuss about circular motion, which is a very important topic in mechanics. Well, in our day-to-day life we see lots of examples of objects which move in the circular path. The earth rotates around the sun, like even when we move on the road and when we take a turn, the path which we follow along the turn is also a partial circular path. You take a bicycle, the tires of the bicycle are actually moving in the circular direction. So there are many examples. So it's very important to understand circular motion very deeply. So in today's video we will discuss the four topics. First is angular velocity, then angular acceleration, and then centrifugal force, centripetal force. Now many people have lots of doubts about centrifugal force and centripetal force, and many have different definitions about these two forces. So hopefully after this video those doubts will be clarified. So let's say I have an object A and this object moves along the circular path as shown by the dotted diagram. So the angular position of the object as shown in the diagram is theta, and the object is at a distance of small r from the center. So just as we had defined linear velocity in our earlier lecture as v vector is equal to the rate of change of linear displacement with respect to time. Similarly, let's define angular velocity as the rate of change of angular position with respect to time. So let me call the angular velocity as omega. Now let's understand the angular acceleration. Well, the angular acceleration analysis will get a bit messy, so just be calm and just follow what I'm saying. I'm sure you will understand it very nicely. So as we can see, this object A moves along the circular path, and we are observing this object A from the ground, which is an inertial frame. So let's say at the point A, let me draw another Cartesian coordinate system, x dash a y dash. So in this plane we have two coordinate systems, x dash a y dash and x o y. Now as we can see, the axes of both the coordinate systems are parallel to each other, so the unit vector will also be same for both the system. So the unit vector along the x-axis will be I cap, along the y-axis the unit vector will be j cap. Now you can see two more terms, er cap and et cap. So what are these terms? So basically er cap is a unit vector along the radial direction, along the direction of change of radius. Et cap is a unit vector along the tangential direction, which is the direction of which captures the change of angle theta, right? Now why do we need er cap and et cap? Well, we need er cap and et cap because whenever an object moves in a circular motion, its position is determined by two parameters, the radius and the theta, right? So these two unit vectors essentially captures the radial direction and the angular direction. Now any analysis you will do in the circular motion, be it angular acceleration or angular velocity, if we find out the components of acceleration or velocity along the radial direction and along the tangential direction, then it simplifies our analysis and it also helps to solve the problem in an easier manner. So that's why we will do the analysis along the radial direction and along the tangential direction. Now let's define these unit vectors in the Cartesian coordinate systems. So er cap, so the magnitude of er cap will be 1 since it's a unit vector, and the component along x-axis will be what? 1 cos theta I cap and 1 sin theta j cap. So er cap will be cos theta I cap plus sin theta j cap. Now as we can see, et cap makes an angle theta with the y-axis. So the component of et cap along the x-axis will be minus sin theta I cap, and along the y-axis it will be cos theta j cap. So et cap will be minus sin theta I cap plus cos theta j cap. Well, now before moving forward, I'll explain few basic concepts of differentiation which will help in understanding our derivation of angular acceleration in a bit easier manner. Now differentiation of sin theta with respect to time will be given by cos theta d theta by dt. This is just the rule of differentiation. Differentiation of cos theta with respect to time will be minus sin theta d theta by dt. Differentiation of a plus b dt will be basically dA by dt plus dB by dt, and differentiation of a into b with respect to time will be a times dV by dt plus b times dA by dt. When you multiply dA by dt with a constant c, then it is essentially same as differentiation of the constant into a, which is dCA with respect to time, dCA by dB. So now the position vector of this object A with respect to the ground will be what? So we will consider the Cartesian coordinate system XOY, which is the coordinate system with respect to the ground. So the position vector of point A with respect to the ground will be OA vector, which will be R cos theta I cap and R sin theta j cap. So the position vector with respect to the ground will be R vector is equal to OA vector is equal to R cos theta I cap plus R sin theta j cap. So what will be the velocity vector? The velocity vector will be obtained by differentiating the position vector with respect to time, which will be differentiating this whole thing with respect to time. So again, which is DOA with respect to time. So if I do this differentiation and follow the differentiation rules which I have just explained, and replace d theta by dt with omega, which is the angular velocity, I get the velocity vector as r omega minus sin theta I cap plus cos theta j cap. Now minus sin theta I cap plus cos theta j cap is basically ET vector, which is the unit vector along the tangential direction. So velocity vector is equal to r times omega ET cap. So what does this mean? When an object moves in the circular direction, then the magnitude of the velocity is given by the radius times its angular velocity, and the direction of velocity will be along the tangential direction. Now let's understand the acceleration vector of the object with the point of observation being the ground. The acceleration vector will be given by differentiating the velocity vector with respect to time, which will be essentially differentiating this entire term with respect to time. Now here in this term, let's say if I assume r omega as a and this term as b, and let's say if I apply this rule of differentiation, which is dAb by dt, then finally I'll get the value of acceleration as given by this equation. Now here I have skipped few intermediary mathematical steps. This you can take it as a homework, and you can derive it. All the information for the derivation are given in this sheet. Now let's observe this acceleration equation very carefully. This equation states that when an object moves in a circular path, the acceleration vector has two components. The first component is along the negative ER direction, which is along the negative radial direction, and the magnitude is given by omega square r. The second component is along the positive tangential direction, and the magnitude is given by d dt of r omega. Now let's understand centripetal force and centrifugal force. Now let's assume that this object is moving at a constant angular velocity. So omega is constant, and let's say since the object is moving in a circle, so the radius will also be constant. So this r omega becomes a constant. The rule of differentiation states that differentiating a constant gives a value of 0. So if an object moves in a circular path at a constant angular velocity, then the object will not have any tangential acceleration. The object will only have a radial component of acceleration, and that component of acceleration will act towards the center of the circle or towards the negative radial direction. Now again, here I must say that we are observing the object from the ground, which is an inertial frame. So in that case, what force will act on the object? The force will be obtained by multiplying this acceleration by mass. So when an object moves in a circular path, and if we observe the object from the ground and the angular velocity is also constant, then the force which acts on the object is given by is called centripetal force, right? And the magnitude of the force is given by m omega square r, and this force acts in the negative radial direction, or rather it acts towards the center of the circle, or it acts in the inward direction. So this is centripetal force. Now let's say we change our frame of reference, and now we sit on the object itself, and then we observe the object. Then what happens? This object becomes, since this object is accelerating with respect to the ground, so this object becomes a non-inertial frame for us, right? So if we do the analysis sitting on the object, then we will have to apply a pseudo force, right? So what will be the direction of the pseudo force? The direction of the pseudo force will be opposite to that of the direction of the acceleration of the object. Since the object is accelerating towards the center or towards the negative radial direction, the pseudo force will act towards the positive radial direction. And what will be the magnitude of the force? The magnitude of the force will be given by mass times the magnitude of the acceleration, which will be given by m omega square r. So centrifugal force is essentially a pseudo force which acts on an object when the object moves in a circular path at a constant angular velocity, and when we observe that object by sitting on the object itself. In other words, when we make that moving object as our frame of reference. Now let's understand centrifugal force with the help of a practical example. So let's say I am sitting inside a moving car and the car takes a turn along a circular path. And when the car takes the turn, I feel an outward force. I feel a force in the outward direction. So why do I feel so? So when the car takes a turn along the circular path, then essentially with respect to the ground, the car accelerates towards the center of the circular path. Now since I am sitting inside the car becomes a non-inertial frame for me. So when I observe myself sitting inside the car, I'll have to apply a pseudo force. The direction of the pseudo force will be opposite to the direction of the acceleration of the car. So since the car is accelerating towards the center of the circular path, the direction of the pseudo force which will act on me will be opposite to that the acceleration of the car, and hence that force, the pseudo force, will act in the outward direction. So this is centrifugal force at work in our day-to-day life. So thanks for watching this video. If you have found this video useful, then please subscribe to my channel. In the next video we will discuss about the application of circular motion with the help of a practical a solved example. So thank you.